So in section 3.4, we're going to talk about measures of relative standing. So far we've talked about measures of central tendency or measures of center. Those were your mean, your mode. You could use something called the mid-range, which is the middle of the highest and lowest. We saw a couple other measures, geometric mean and harmonic mean. But some measure of the center. We talked about measures of variation, how far things are spread out throughout the data set on average. Now we want to be able to look at an individual value of data. How does this compare to the rest of your data set? And to help reflect how far apart things are or how far a value is from the center, we're going to calculate something called a z-value. Z-value. And the z-value is going to be calculated by this. You're going to take your piece of data, so your data value, minus the mean and divided by the standard deviation. Now let me give you some symbols for that. So right now what we've dealt with is stuff like this. We've used X to symbolize our data. X bar is the sample mean, and S is the sample standard deviation. Now these are just estimates. If you're sampling from a population and you want to try and find out the bigger picture, these are just estimates of your population values. So if you happen to have population data, then you'd be calculating it as X minus mu, mu. This is a Greek letter, divided by sigma, which is your population standard deviation. So this is your population mean. And this is your population standard deviation. Quite often we don't have these numbers, so we use our best guess, which is the sample mean and sample standard deviation. Basically what you're doing is you're counting how far away you are from the center, and that's going to help you determine how unusual you are or are not. So for instance, IQ. What's IQ stand for? Anyone know? Yeah, intelligence quotient. Intelligence is supposed to have a mean equal to 100 and a standard deviation, depending on the author of the study. Let me round it up to 20. I've heard anything from 10 to 20. But let's look at Marilyn Vos Savant. We talked about her the other day. In fact, let me do a quick Google search while you look that up, or while you copy that down. So let's do it here. Marilyn Vos Savant. There we go. What's it say about her IQ? IQ. Does anyone see it here? Hoping I don't have to go too far in here.
Is that where the term savant comes from? Or is that just personally?
I think, I've heard savant even replied to some autistic people who have some really exceptional skills in one direction or another. Here we go. 228. Wow, that's in the stratosphere. That's pretty high. So let's try and find the z-score for her intelligence. So the z-score would be 228 minus 100 divided by 20. So that gives us 128 divided by 20, So that's going to be about 6.4 if I do my math correct on that one. 6.4 standard deviations above the mean. That's huge. It's way, way out there in terms of intelligence. So imagine if intelligence has that bell-shaped distribution, let's look back at our empirical rule. 99.7% of the data is within 3 standard deviations of the mean. Imagine how far out 6 standard deviations or 6.4 standard deviations would put her. I mean, that's just really, really rare air up there. Let's do a couple more here, this time from the book, problem number 14. As of this writing, Sandra Bullock was the last woman to win Oscar for Best Actress. Jeff Bridges was the last man to win for Best Actor. At the time of the award ceremony, Sandra Bullock was 45 years old, and Jeff Bridges was 60 years old, based on data set of .11. All right, so they're giving us the relevant information here. Best actresses have a mean age of 35.9 and a standard deviation of 11.1. So let's find the Z-score for Sandra Bullock. So problem number 14, Sandra Bullock. Z would equal 45 minus 35.9 divided by 11.1. Now, one thing about Z-scores that I'd like us to always do is round Z-scores to the nearest 1/100th. Always round to the nearest 1/100th. Now, it's probably something that drives some of my algebra students a little bit crazy. I'm always specifying one number or another, not as consistent as I'd like to be. If I had a conscience, that would worry me, but I'm okay. All right, feel free to laugh. Remember, this is live. In any case, with Z-scores, we can be very consistent, and there's a good reason for that. Later on, we're going to be working with Z-tables, and the Z-tables are going to require exactly 2 decimal places to the right, or 2 digits to the right of the decimal. So we're always going to round this to the nearest 1/100th. I think we can do this one without Google Sheets. Parentheses 45 minus 35.9 divided by 11.1. So 0.8198, etc. But when we round that to 2 decimal places, it's going to be 0.82. One thing that's important when you're calculating Z-scores is to have the order correct. It's always your data minus the mean divided by the standard deviation. The reason that's important is because if you subtract these in the wrong order, you could get a different sign. What do you think a negative Z-score says about your piece of data? What has to happen if you get a negative value for the Z-score? Let's take a look at how it's calculated. You take your data minus this divided by S. Now, S is a standard deviation. It's always positive. So whether or not your Z-score is positive or negative really is going to reflect what's happening in the numerator. It'll only be negative in what case? What has to be true here?
The mean is greater.
Yeah, the mean is greater than your value. So you're below the mean is what a negative Z-score says. A negative Z-score reflects a value below the mean. Okay, let's You want to calculate another z-score, or are we okay with just 2 examples? Z-scores are easy calculation? One more? Okay. There's a second part in this one, is to calculate the z-score for Jeff Bridges. The mean, Jeff was 60 years old when he won the Best Actor Award. The average age for men, X bar, would be 44.1, and the standard deviation there is 9. So why don't you see if you can't put that together to calculate the z-score. So the calculation should look like this. Your z-score is going to be 60 minus 44.1 divided by 9. Now, it's not something that you really need to worry about. Learning a little finesse: if you hit the second or the alpha key, then the y equals key on your graphing calculator, then it gives you kind of a normal fraction like we would write. So 60 minus 44.1 divided by 9. Where am I going to round that to? What's the correct z value for an? Yeah, 1.77. So about 1.77 for the z value there. Let's revisit the empirical rule here. Remember, the empirical rule says that most of your data is going to be within 2 standard deviations of the mean. So let's apply that to designing aircraft seats. So it's going to be problem number 10. So in the process of designing aircraft seats, it was found that men have hip breadths of 36.6 centimeters and a standard deviation of 2.5 centimeters. Inches, sorry. You know what? That's not right. This has got to be centimeters. 36.6 inches would be really amazingly big. So I'm guessing that they both should be centimeters. What are the z-scores that separate the unusual hip breadths from those that are usual? And then unusual from those that are usual. So the typical values are going to be within 2 standard deviations. So typical values are x bar minus 2 times the sigma and x bar plus 2 times standard deviation. I said sigma, that's just habit. That's your Greek letter for the population standard deviation. Well, they give us this information. X bar was 36.6 and S was 2.5. And we're going to assume those are both in centimeters because I don't think we're that big of a population. So 36.6. Now, you can do this part in your head, although I won't. It's going to be 2 times the standard deviation. So you should get 31.6 as the lower limit. What's going to be the upper limit? 41.6. 41.6. Which of these should you choose if you're designing the seat? What should you choose to be the width of your seat? 41.6? 31? Why? Yeah. You want people to fit in your seat, so you're going to go with the higher one. That way most of the people, unless you're United Airlines, and then you don't care, right? All right. All right. Easy. All right. Yeah, so these are going to be your typical values. Anything outside that's going to be atypical, at least for men. All right. One of the things that I really kind of like about using Google Sheets to do this next part is that it's going to be so much easier than what we used to have to do by hand. It's such a pain. And it's called percentiles and deciles. It's a different way to look at data and discuss your position within a data set. So let's start with quartiles. Quartiles separate the data into how many parts? 4. How many quartiles are there? 3. There's 3. You need 3 points to separate your data into 4 parts. So Q1 is going to separate the lowest 25% from the upper 75%. Q2 separates the lower half from the upper half. Now Q2 has a different name. We haven't really mentioned it much or discussed it much, but it's the median. So it's the median. The median is what separates the top half from the bottom half. If you pay attention to government statistics, what you'll find quite often is that when they discuss income, that they typically discuss median family income. Why do they discuss median family income? Why don't they look with the mean? What would be the problem of working with the mean family income? Yeah, some of the outliers, right? If you average me with Warren Buffett, you're going to get something that makes no sense, right? It's just not going to be reflective of anything. Basically, you'll be taking Warren Buffett's income and dividing it by 2, all right? Because mine will be like 0 compared to him. So the mean, remember, the mean was sensitive to what? Yeah, to extreme values. So the median is just the middle number. And whatever happens out at the ends, with Warren Buffett or with me down here, is not going to affect where the center is. So the government keeps track of median family income. Where's the center on that? You don't have to divide things up into just quartiles. We can divide it up into smaller units. Deciles. You can divide it up into chunks of 10. And of course you would have correspondingly 9 deciles. And then we can go a little bit further into percentiles. And percentiles are dividing it up into little chunks of with 1%, where your data is. So let's talk about percentiles a little bit and draw some associations. So Q1 separates the lower 25% from the upper 75%. Q2 is the middle or median. Separates the bottom 50% from the upper 50%. And then Q3 separates the bottom 75% from the upper 25%. There should be 25% here. Now we're not going to work, we're not going to get our hands on deciles, although we can. Let me break this down into percentiles. Q1 is also P25. Q2 would be P50. And Q3 would be P75. These are percentiles. So it's what separates the bottom 25% of your data from the upper 75%, and so on. And Q2, remember, has that special name of the median. Okay, so let's actually look at some data. Let's see here. Triola. Okay, so if you happen to have it handy, great. If not, it's not a big deal. These are the body temperatures from Triola's data sets. And let's find some numbers here. Let's find some of the quartiles. So in Google Sheets, I think the command is this. Type in equals and then percentile. And then you need to type in two things. So after you type in percentile, you're going to select your data. So that's my data here, comma. Now you need to choose what percentile you want. Do you want the 50th percentile? Do you want the 75th, the 25th? What do you want? So whatever percentile you want, you have to type that in as a decimal. So if I want the 23rd percentile, then I type in 0.23. If I want the 73rd, then I type in 0.73. So throw out a number. What percentile do you want? 37. So let's type in 0.37. And there you go. So 98 is in the 37th percentile. That would separate the lower 37% from the upper 63%. So it's nice. I used to hate this before we had this available. I mean, the procedure for finding these numbers was just so tedious. And now it's at a push of a button, so that's kind of good. Now, what would I expect you to know and do on a test? I'm not really worried about you doing the calculation. I'm more than happy for you to do it online or in a spreadsheet or whatever. But what you should be able to tell me is what those mean. So suppose that this was your score on the ACT. Would you want to be in the 20th percentile or the 80th percentile? 80th, right? You want to be near the top. You want to be closer to the top than the bottom. So that's the kind of thing that I want you to know. And that's the way we're going to that's the way I'm going to probably write your test, is asking you questions like that. Do you understand what it means to be in the 73rd percentile as opposed to the 27th percentile? Which one is where you want to be depending on the circumstances? So else about relative standing?
Body temperature would you want to be at the 50th percentile?
Um, that's a good question. Uh, Here, I guess I'd just want to be near the middle someplace. I don't want to be running too hot or too cold. So it's a good question here. Let's apply the empirical rule to that after I answer this question.
Are you going to put like a old test online so you get
I will. I will put some old tests online. I gotta caution you that this is the first time I've taught this course with Google spreadsheets. So the old test will be helpful to an extent, but I'm gonna have to change things up a little bit because of the way we're teaching this. So, I mean, one thing that you won't have to worry about is a lot of hand calculations. Those will be gone. So that's a real good thing. What you should concentrate on is on the big picture. You know, understanding the difference between the 20th percentile and the 80th percentile, and knowing which one is where you'd want to be depending on the circumstances. Those are the kinds of questions I anticipate asking. So, Abby? No, Mira. Sorry.
Is the SOAR test going to be on paper then?
Yes. Yes. I don't know what to do about the computer part of that. Yeah. So right now, I guess in my mind, until I figure out something different, is that it's just going to be completely on paper. All right. You should bring a calculator. If you don't have a good calculator, I can borrow you one. But that's all you count on. Does everyone have a laptop or a tablet they could bring in if they needed to? Okay. All right. So, I mean, it might be able to open things up a little bit. Megan?
Could you do that one more time? Because I missed how you got the percentile.
Oh, sure. We'll tell you what. Why don't you pick what percentile we want to calculate? The 20th percentile, the 12th? What do you want? All right. So, you choose percentile. Then you select your data. And then you put a comma here, and then you type in the percentile as a decimal. So 20% is 0.20. So 0.20. And there you go. So 20 percentile, 97.6. So you're running kind of cool there, but hey, maybe that's the way you work. Another problem with the original study that they did on the average human body temperature is that it fluctuates during the day. It's what I think it's the fancy term is diurnal. So it's different in the morning and different in the evening. So unless you're taking account of that, your results aren't going to be very good. So I feel bad. I want to say that guy who came up with a 98.6 average calculated or measured temperatures on like 100,000 people. It's in the multiples of 5 figures at least. It's unfortunate though that his data wasn't really worth that much. Okay, let's finish up with, since I've got this data here, let's do one more version of, the what's typical here. So you don't have to copy this on your sheet. What I'm going to do is just find the average of this data set of body temperatures. So average of, I think I can just do it this way, column A. No, didn't like that. All right, let's try it again. Equals average of that. So there's your average. So about 98.2, and the standard deviation. Got to type in equals STD standard deviation. So let's find out what's typical for this data set, and then see if there's any unusual values for us. So standard deviation of 0.623, roughly speaking. Now, what's typical? What's typical is your range from 2 standard deviations below to 2 standard deviations above. So let's calculate that range. We'll do it here. We'll say that's equal to this minus 2 times this standard deviation. And then I'll do the same thing here, equals this plus 2 times the standard deviation. So the typical range for this data set is going to be 96.94 to 102 or 100.2. So if we look at our data set, there's really only 2 observations that don't fit in what's typical. 96.5 and 96.8. Boy, that's running real cold. All right, definitely unusual on those. Any thoughts before we finish up here on measures of relative standing? Okay, let's take a break here for homework. Try problems 1 through 31. So homework 1 through 31, that's section 3.4.